So our next speaker is Gemma Rate. And over to you, Gemma.
Brilliant, thank you. So, yeah, I'm Gemma Rate from the University of Sheffield, and I'm going to be giving you a quick overview today of the work that I've been doing on Galactic Wolf-Rayet stars and Gaia DR2. So first, a quick introduction to massive stars in general. We mainly consider a massive star to be any star that's over 8 times the mass of the Sun at birth. And because they're so massive, these tend to have very short lifetimes, less than about 50 million years. They also have very high temperatures and correspondingly extremely high luminosities. And because they form at the extreme upper end of the IMF, they're much less than 1% of all stars at birth. So even though they're so rare, high-mass stars have a very big impact on the galactic environment. They generate alpha-process elements, most notably oxygen, but also carbon, neon, etc., through both fusion in their core and their deaths as supernovae. They also generate a lot of the mechanical feedback that is responsible for quenching star formation in some areas by driving out gas with their stellar winds, and again with their deaths as supernova. And if I can get this to work, there we go. You can see an example of this with a big wind-blown bubble near the young massive star cluster Westerland 2. High-mass stars also produce ionizing photons, most notably ionized hydrogen in H2 regions, and they're also progenitors for dual neutron stars and dual black holes, which, as you know, can go on to produce gravitational wave phenomena. They're also potential progenitors for long gamma-ray bursts. So massive stars have a bit of a specific birth and evolutionary trajectory. We believe that they're born overwhelmingly close to the galactic midplane, only having very short scale heights of about 50 parsecs or so. They can be ejected from their birth location, and I'll go on to talk a little bit more about this later on. But when they are ejected, it can be at very high velocities, so over 30 kilometers per second. And we refer to those stars as runaways. We believe that massive stars are mainly located in clusters and associations, preferentially, and this is because their short lifetime means they die before the cluster can dissolve over time. Most notably, anywhere up to 70% of high-mass stars are actually born in binaries, and this has a major impact on their evolution and is actually one of the big sort of open questions of massive star research. So coming on to the very specific type of star that I look at, a Wolf-Rayet star. So this is the kind of core helium burning stage of the most massive O stars, so stars with an initial mass at least 25 times that of the Sun. Because they're so massive, they have very strong stellar winds and therefore high mass loss rates, and these act to blow off their outer layers of atmospheric hydrogen. This reveals like very broad emission lines, most notably in helium, nitrogen and carbon. And obviously because they form at the extreme upper end of massive stars, they're a very good tracer of massive star birth and evolution. So, going on to discuss a bit about Gaia DR2 specifically, obviously we need distances to be able to properly study Wolf-Rayet runaways, the fraction in clusters and associations, and the specifics of individual Wolf-Rayet stars themselves. And unfortunately, before Gaia DR2, we only had access to a parallax of 1 Wolf-Rayet star from Hipparcos. But luckily, Gaia has expanded that sample vastly to almost 400 Wolf-Rayet stars. So as per the suggestions in the Gaia data release papers, we've used Bayesian methods to go and then calculate the distances to these Wolf-Rayet stars. Now, there has been some work already done by Baylor-Jones et al. Looking at the distances to the entire Gaia catalogue. However, unfortunately, because we're looking at a very, very specific subset of stars with very specific locations, they have a different distribution to the population as a whole. And therefore, we could probably get different results if we used a very specific prior. So I've got a kind of an example, shows up ish on the screen that you can see at the moment. So these are kind of galactic coordinates. We've got the sun at the centre and the galactic centre at about 8.1 kiloparsecs. And on the left, you can see what we've used is a distribution of H2 regions. As I mentioned, high-mass stars do ionise H2 regions, so it forms a good rough tracer of where we could expect to see those. And that's actually from the radio originally. And then on the right, we've created a map of extinction based on some dust models that we've used. And you can see that that gives you very high extinction towards the galactic centre, decreasing as we go outwards. And we mainly needed that because, as I say, our initial H2 regions were looked at in the radio. So we wanted to approximate more what Gaia is going to be able to see. So combining those two inputs into one prior and then getting out the distances by combining that with parallaxes, we get about 381 Wolf-Rayet stars out of the 650-odd known stars in our galaxy. And we can plot those nicely again on another radial map here. And you can see that they start to nicely trace out the galactic arm here. So also on this plot, we've plotted a couple of examples of error bars that we have on these distances. And you can see here how, as we go further and further from the sun, unfortunately, the quality of the parallaxes lessens a bit because the relative parallax error increases, and so correspondingly our distance estimates fall over a larger possible range. We also then took those distances and were able to calculate roughly heights above the plane for these Wolf-Rayet stars. So using those distances, we then went on to look a little bit about cluster and association membership to see which of our Wolf-Rayet stars were in those populations. And so we ended up using other cluster members from about 27 different clusters, which you can see here plotted in grey, and the Wolf-Rayet stars are plotted in red. And we then compared the proper motions of the Wolf-Rayet stars to the rest of the cluster members. And you can see for this particular example, Trumpler 27, everything's nicely kind of clustered together and bound properly. And the Wolf-Rayet stars actually do also fall into that, so they're actually most likely members of this cluster. We also, as you can see on the top image, used our distances as kind of another double check for that, to check everything was roughly in the cluster at the right distance that we'd expect. And again, you can see that the two red Wolf-Rayet stars fall within the generally acceptable bound with all of the other cluster members. So doing this for all of the clusters and associations that we had a look at, we find that only about 10% of our sample of detected Wolf-Rayet stars were confirmed as members of the cluster, and that unfortunately fell to only about 3% in the associations. And this was because our search was mainly hampered by things like large scatter in some of the proper motions, which made it quite difficult for us to determine where the kind of main proper motion of the cluster and association was. And unfortunately, some particular clusters and associations had very few members, which again made it difficult for us. But overall, even taking that into account, we can see that Wolf-Rayet stars form generally in more isolated environments that we would expect. And this actually kind of holds true for one of our most closest Wolf-Rayet star, Gamma Velorum, which is found in an environment with very few other high-mass stars. It's the only Wolf-Rayet star. So we then went on to look at distance from the plane, and you can see from this histogram plot that I've made that Wolf-Rayet stars are overwhelmingly located near the galactic midplane. And then we had a look for stars that could potentially be runaways, because for them to have reached a certain height above or below the plane, they would have to be travelling quite fast over their very short lifetimes. And the cut-offs we used for that was about 150 parsecs. And this is because it's about 3 times the H2 region and Wolf-Rayet star scale heights. Now, there are 2 main mechanisms to produce runaways. The first one is a disruption of a binary by a supernova, and if the binary becomes unbound, that can produce a single Wolf-Rayet star, or if it stays bound, a Wolf-Rayet star and a compact object. Or they can be ejected from compact clusters, and that can produce another single Wolf-Rayet star, or this time a Wolf-Rayet with an OB companion. So we found only, again, about 10%, 40 stars of our detected sample were above the 150 parsec limit. 13 of those were known runaways, which was quite good for us to confirm. Only 3 of them, unfortunately, though, have OB companions, and the other 37 stars that we detected, we think are likely single. So we unfortunately can't exactly disentangle which the dominant mechanism producing runaways is. But as we found so few Wolf-Rayet stars in clusters, we believe that this leads us to think that supernova likely dominate the production of these runaways. And because of the excellent Gaia DR2 results and distances that we've got, these are the most robust results for heights of Wolf-Rayet stars so far. So just a quick summary of what I've spoken to you about. We've got distances to 381 Wolf-Rayet stars in the galaxy. We found that cluster and association membership is only about 10 and 3% confirmed respectively, and that's lower than we were anticipating. And at least 10% of Wolf-Rayet stars are potential runaways because we were just mainly looking up above and below the galactic plane. And those were most likely binaries that were disrupted by supernovae. So for our next steps, we're going to be using these distances and previous results we've had of apparent magnitudes to try and go back and see if the absolute magnitudes we get for different Wolf-Rayet stars are sensible, so then we can hopefully verify this work. So yeah, thank you.
So, any questions? While other people are thinking, I had one.
Okay.
So, you've got fewer stars in clusters. Mm-hmm. Could that be related to the fact that you've got a lot of runaways? Because won't they then leave the cluster? So,
the fraction of runaways among Wolf-Rayet stars is generally quite low, only about, as I've mentioned, 10% or so. And because we think so few are being ejected by dense clusters, this probably means that the reduction of the number that we see in clusters isn't down to runaways, it's due to probably formation. But as well, you have to have, as I mentioned, quite a dense cluster for a runaway, ejection-based runaway to occur anyway, so there's not so many of those. But thank you.
Okay, any other questions? I guess not. You've obviously satisfied everybody.
Oh, thank you.